All right, today is February 2nd, 2021. We are now going into the next lesson. We just completed RT210E, which is acid-base chemistry. For the most part, the students did very well on this test. Very pleased. Some of you missed some things that just because you looked at it wrong or whatever, but for the most part, the ABGs, the interpretation of the ABGs were really well. Most of you did really well, didn't miss any of those. And that was very, very important. Okay. All right. So we're going to go in today into the next lesson, which is gas physics, talking about the actual gases that are in the atmosphere. Remember, I showed you a little bit of that last term or last lesson when I talked about oxygen, carbon dioxide, nitrogen, and argon. And then the trace gases that are also found in the atmosphere. But we're going to go deeper into that now because they make up the barometric pressure. So we'll talk about that. How do those percentages equal up to a pressure, and how do we convert it from percent to pressure to see how they add up to the barometric gumbo? Okay. All right. Also, keep in mind that there will be at least 2 or 3 ABGs on every test going forward. All right, so just because you got through this one, you need to make sure you continue to practice your ABGs so they'll always stay fresh on your mind all the way through. So when you get to the final and have about 20 of them, you won't be lost. Okay. Once you have it, it's like riding a bike. You got it. Right. And most of us at this point have it. All right. Today is Tuesday, right? And if anybody requesting for tutoring today, and then the next tutoring will be Thursday. If you want to do tutoring on Tuesday or Thursday, all you have to do is log into the Zoom at 10 o'clock. I go in for a little while to see if anybody logs in. If they don't, then I leave. Okay. But if you want to do it, you need to, be there at 10. You don't have to necessarily let me know, hey, I'm going to sign up. Just be there. Okay. But if you let me know, hey, I'm trying to be there, I'll be there not 10, but 10:05 or 10:15 or whatever. Let me know something and I'll stay on. But if I don't have any requests or anybody who even tries to log in, then I'll move on. Okay. All right, let's look at some of the objectives to this lesson. Gas physics, talking about how gases in the atmosphere work. And then in particular, the respiratory gases that we use, which is carbon dioxide and oxygen, how they work, right? How are they stored? How are they delivered? And how do we figure how much is left in those cylinders that we see? You're going to learn the different sizes of the cylinders and what they mean, how to figure out how long oxygen will last on those specific cylinders. Okay, so let's look at the objectives. All right, so in this lesson, the student will be able to describe Avogadro's law relating to a mole of oxygen. So now you got laws again. You need to make sure you're putting your laws on one sheet of paper. We had Laplace, we had Poiseuille, right? We had Henry, Graham, and now we're talking about Avogadro. Avogadro. The mole is what I call it. Like a little mole in your backyard named Avogadro. He talks about a mole of oxygen. Okay. Relate Dalton's law. It's another law. Dalton's law to the partial pressure of oxygen in the atmosphere. All right. Recall the concentration of oxygen in the atmosphere and lung. Be able to apply the alveolar air equation. Now, you've had the alveolar air equation, so this will be a welcoming overlap. Okay, he's going to talk about that alveolar equation more in depth in this unit and how we arrived at those numbers. Okay, I told you that the barometric pressure was 760, but you didn't know how we got to 760. And so now you're going to find those type of things out. Okay. Relate ideal gas laws to situation use of gas delivery. Discuss the agencies that regulate gas administration. Everybody has their hands in the pot, okay? You got a agency that conducts how the cylinders are made. You got agencies that talk about or control or govern how they are moved, stored, all those things. Okay. You have safety systems for them that are different. And so it's a lot of things to learn. This is not as hard as the last unit, but it is very informational. And you will need to know how to do this. You will have a lab with this one. This is the next section that has a lab. So when you come on test day for this, you need to make sure you're on time so you can take the test and then go over and check off on the lab. That will be putting a tank, or we call them cylinders, turning it on and turning it off. All things that go with using one and taking it apart. Okay, that will be the lab for this one. Uh, Recall the color codes, mandatory for E cylinders. The E cylinder is the E tank or cylinder that you see when people are at the casino, people who are on at the grocery store, at church. The one that they roll beside them, that cylinder is called an E cylinder. Okay, and they are mandatory color coded in the country by law, so that you don't, because you might have somebody who's not paying attention or can't read. They need to know what color is for oxygen, what color is for something else. Okay. Differentiate between the safety systems. Demonstrate the recognition of cylinder markings. Each cylinder has markings on them. You need to know what's usually on the front of the cylinder, what's usually on the back. Calculate duration of flow of the E, G, and H cylinders. That means how long will that flow last? If I have him set at 2 liters per minute, well, how long will that 2 liters last in that cylinder? That's a formula that you'll have to recall. Demonstrate safe handling of the cylinder. Discuss cylinder testing. How often are they tested to ensure that they are safe for the patient? Recall the difference between liquid and gaseous oxygen. Oxygen comes as a liquid or as a gas. Starts off as a liquid, turns into a gas. You'll understand why and how that happens. Differentiate between single stage, multi-stage, present and adjustable flow meters. Flow meters. All right. You have to be able to tell what's compensated and uncompensated for the flow meters, not the ABG, just the flow meters. Some flow meters are compensated, some of them are uncompensated. You want to tell me, how do you know which one is which? Make adjustments when using oxygen flow to deliver helium and oxygen mixtures. Helium is a gas, right? And it also can be used with oxygen, okay? Describe the function and advantages and disadvantages of the Bourdon gauge. And then in the lab, you have to make sure you're able to correctly select the right E or H cylinder, correctly maneuver the cylinder around the cart and all that, attach it to start it, and detach it to get rid of it. We'll learn that as we go. All right, so you see, it's a nice little amount, but you can do it. All right, so the presentation starts right here. And it's also in the module as a PowerPoint. You have a PowerPoint in the module that you can look at. It follows right along with this lesson plan. So first we'll start off with the states of matter. We all know that matter is in 3 different states, either solid, liquid, or gas. If it's something that is solid, it can be heated up like ice. Let's just say water. When water is cold, it's a solid, right? When we heat it up, it'll turn into a liquid. If we continue to heat it, it will then turn into a gas. Okay. Now, what are gases? Gases are molecules that are continuously moving. Molecules that are continuously just moving around in the air. That's the gas. Here's your first law. Avogadro the mole. Avogadro says that 1 gram atomic weight of any substance contains 6.02 times 10 to the 23 atoms. And this is known as 1 mole. He said everything, any substance on Earth, if just take 1 gram of any substance on Earth, and it will have 6.02 times 10 to the 23rd atoms on it. And that is considered to be 1 mole. Okay, that is what a mole is. And I call him Avogadro the mole to help me remember his law. All right, now 1 mole of gas at STP. What is STP?
Would it be the standard something pressure?
Yeah, standard temperature pressure. Standard temperature pressure. They're trying to let you know because pressure and temperature, when they're all things change, okay? Those things have to be accounted for. The pressure, the temperature have to be accounted for because if they're different for whatever reason, it can change the whole outcome. Like the PB is usually 760, but if it's something different, that's a different pressure, it makes the whole problem different. It will adjust for that. So you have to understand that temperature, volume, and pressure are very, very important. If they change, the game changes. Okay. So what he's saying is that if you take 1 gram of any substance will have that amount of atoms on it, 6.02 times 10 to the 23, right? Those many atoms on any 1 gram of any substance, any mass or matter, okay? And that amount of atoms is called 1 mole, okay? And so what he says is now that you understand what a mole is, then he's saying that mole at standard temperature pressure, see, 1 mole of gas at standard temperature pressure will occupy approximately 22.4 liters of space. All right, so that is Avogadro's law. You need to know his law, but you won't have to figure out the 6.2 to 10, how many atoms is that and all that. You won't have to do that. You just need to know what Avogadro's law is. All right. Next lesson is pressure. Pressure. Remember we talk about pressure all the time. And there are 2 pressure measurements. What are the 2 pressure measurements? Huh? No. 2 pressure measurements throughout the whole millimeters of mercury, which is usually inside the body, and
Millimeters of water.
no, not millimeters of water.
Oh.
Centimeters of water. Centimeters of water. So we have 2 pressure measurements in respiratory, right? In the world. And they are millimeters of mercury and centimeters of water. Remember that the millimeters of mercury is usually the pressure that are found within the body, like blood pressure is measured as millimeters of mercury. The P(a)O2 is the partial pressure of arterial oxygen. It's in millimeters of mercury. The partial pressure of CO2 is millimeters of mercury. It's a pressure inside of the body, okay? But when we start talking about outside pressures that we're doing to somebody, okay? Pressures that we're delivering to somebody is usually in centimeters of water, Okay. Now, that's not to say that every single thing is in the body if it's millimeters of mercury. I'm just telling you, it's usually for the most part, those are pressures inside the body. So if you're not sure, think about that. Okay. But PB, also known as P bar, right? PB and P bar is the same thing saying barometric pressure. The barometric pressure is the pressure that is around you right now. The amount of pressure that's pushing on you from the atmosphere. Okay. Normal barometric pressure is written as 760 millimeters of mercury or 14.7 psi or 1,034 centimeters of water or 33 feet of water. So they're saying that's the pressure at sea level. Okay. About sea level, the barometric pressure is about 760. Okay. About sea level. So 760 will be considered 1 atmosphere. If we start thinking about going in the diving, and we can go down 1 atmosphere, 2 atmospheres. You know, the farther you go down, the farther you go down in the water, how much heavier is the water on you? Does the water on you get heavier or does it get lighter as you go deeper into the ocean?
It gets heavier.
Heavier. It gets heavier. All that weight of the water is getting heavier on you per square inch, right? And so that's that barometric pressure in the deep is really, really high, right? But what about when you go up high into the mountains? That pressure gets thinner, okay? It gets lighter on you, okay? So the barometric pressure above sea level is lower than 760. 760 is right there at sea level. As you go down deep, it gets higher. As you go up high, it gets lower, okay? That's why it's harder for people to breathe when they're up high, because remember, the only way for gas to move from outside to in your lungs has to be a change in pressure. And not only just a change in pressure, but your intrapulmonary pressure must be lower than the atmospheric pressure. So if you go up super, super high and the atmospheric pressure is now being reduced, and that means you got to work harder to suck in some air. Okay. All right. So normal barometric pressure, this number here, mainly you're going to see 760, but you may see all of these except. Know that normal barometric pressure is not only 760 millimeters of mercury, but it's also 1,034 centimeters of water if we were to convert it. Or if we were to convert it in feet, it would be 33 feet of water. Or if we were to convert it into PSI, it would be 14.7 PSI. Pressure per square inch, or pounds per square inch. All right. Like the pressure inside your tire is in PSI. Okay. Pounds per square inch. So when you inflate your tires to 44 PSI, that means for every square inch of your tire is 44 pounds of pressure pushing against that. Okay, that's why if you pop it, it blows. There's a lot of pressure. 44 pounds is a nice little amount. So you imagine a 18-wheeler's tire or one of those excavator tires that are super big. If they pop, they can kill somebody. All right. So now we're kind of going to be getting into the alveolar air equation. Okay. We're going to get into the alveolar equation to kind of understand that each and every component of the alveolar air equation. First thing they talked about was the barometric pressure. We know that's the pressure at sea level, which is about 760 millimeters of mercury. But then we said that water vapor also has a pressure. Okay, that water vapor exerts its own pressure. So water vapor, also known as humidity, exerts pressure. And we know that the partial pressure of water at 100% relative humidity and 37 degrees Celsius is 47 millimeters of mercury. That's where they got the 47 from. Okay? We know for a fact that at regular normal body temperature, at a relative humidity of 100%, which you'll learn relative humidity later in when you get to the next session, which is aerosol and humidity, the partial pressure of water vapor is 47 millimeters of mercury. All right, now we get into Dalton's law. Very big law. Dalton's law, and I'll read it to you on here, and then I'll give you my definition. The sum total of the individual partial pressures of gases in the atmosphere are equal to the barometric pressure. All right? What I'm telling you is Dalton's law is the barometric gumbo. Okay? Barometric gumbo. When you eat gumbo, you go, you know, if you say gumbo, you say soup, whatever. They have a lot of different ingredients in it, right? When you take a spoonful of it, it has one taste, right? So, that gumbo is good. That's my mama gumbo or whatever. You taste it, it has a taste. But what Dalton says is the same thing with the atmosphere. The atmosphere with all of the gases together have one pressure. And that pressure is the barometric pressure, which is 760, okay? But if you were to take each and every ingredient out of that gumbo, if you took the carrots out, the carrots taste like carrots. If you take the sausage out, the sausage tastes like sausage. If you take the rice out, whatever else is in gumbo, right? Shrimp out, it tastes like shrimp. So he's saying that every gas in the atmosphere has its own pressure. It exerts its own pressure. And when you put them all together, they add up to one barometric pressure. Okay? It's like getting on the elevator. Everybody in the elevator have their own pressure, or own weight, right? If I get on, I add some weight. If somebody else gets on, they add some more weight. When everybody is on, that total weight will be the barometric pressure, right? That's the total weight. But if I take one person out and this person out, each individual person have their own weight. Okay? So that's all he's saying. And if you look at the board, we see that the atmosphere, which I told you the other day, is made up of oxygen, carbon dioxide, nitrogen, argon, and trace gases, right? We know that oxygen is about 21% of room air, right? Carbon dioxide is about 0.03% of room air. Nitrogen is about 78% of the room air. That's the most, right? Argon, 0.93%, and trace gases like farts, okay? That's the farts of the world, just small amount. They are about 0.01% of the atmosphere, okay? Each one of these different gases are floating around in here right now at their own respective percentage. Room air is 21%. That's actually 20.95, but we go with 21%, okay? Now, how then, Mr. McCarthy, does oxygen being 21% measure up to a pressure? It's not millimeters of mercury, that's percentage. So how do I change the percentage into a pressure? Well, I'm glad you asked. It's simple. Just like this. Good and close to you. All right. Oxygen. 21% of the atmosphere. If I want to know what that is as a pressure, because all of the atmospheric gases together make up what pressure?
Barometric.
Barometric pressure. All of the atmospheric gases, when they exert their pressure, they make up one pressure, and that's the barometric pressure, which is how much? 760 at sea level. Okay, at sea level. So, well, how do I know how much pressure oxygen is is putting in? How much is he pushing? I don't know. I don't know if it's a percent. I don't know how much that's contributing to the 760. Well, all you do is do this. 760 times 0.21, and that will give me the pressure of O2. Somebody do that. 760 times 0.21. Need a calculator? Okay. So we're going to be doing some calculating, so make sure y'all got your calculators out. 21.
Wait.
No, you need one back? You got one?
I got one.
Okay.
It's 159.6.
All right, so 159. We usually say 159. So 159 millimeters of mercury. Oh, so oxygen, O2, is 159 millimeters of mercury. All right. Don't forget we had to change that decimal. Move that decimal. Remember, 21% is 0.21. Two places to change it from a percent to a decimal. You move the decimal two places to the left. Okay, don't forget that. All right, so that's oxygen. Oh, okay. Now I know that oxygen is pushing 159 of that total 760. It's only 760, and oxygen is pushing 159 millimeters of that by itself. All right, well, let's see what else they're doing. Who else is pushing? You know, or how much are they pushing? Because everybody's pushing. Every ingredient has its own flavor. Okay. All right, so that's oxygen. The next one, let's just say CO2. CO2 is 0.03%. How much pressure would that be? I would have to do this. All right. Carbon dioxide. Well, no, I'm sorry. I would have to do this. 760 times, what would I do with times what? No, that's a percent. I got to turn that into a decimal.
3.
Go two places to the left, whoever that was, whenever you change it. I know it's in decimal form, but it's still a percent. So to make it pure decimal, you got to move two places to the left. So that would be 1, 2. And then throw a 0 right there. So now we have to have 0.0003 times 760. And that gives us the pressure of CO2 in the atmosphere. What is that? 0.228 millimeters of mercury. So see, CO2 is not pushing a lot, is it? CO2 is only pushing 0.228 millimeters of mercury of the total 760. All right, so CO2 is 0.228 millimeters of mercury. All right, the next one we're going to do is nitrogen. Nitrogen is 78% of the atmosphere. Well, if nitrogen is 78% of the atmosphere, how much pressure is nitrogen exerting in the barometric gumbo? All right, so I want y'all to do that and tell me.
592.8.
Okay. 592.8. So what we did, we said 760 times what? 0.7.
78.
And that gave us how much? 592.
92.8.
Millimeters of mercury. That's a lot. That's almost all of it. So what two gases exert the most pressure? Nitrogen and oxygen. And you're going to learn, that's very important. Why there's so much nitrogen? You want to learn why? Because the nitrogen is what keeps the alveolar walls open. In order for gas to exchange, the alveolar walls have to stay open, right? Oxygen can't take the time to open up the walls and exchange, right? So it's got to be something in there that will hold the walls open while y'all do y'all's business, right? You and CO2 do your little business. I'm going to hold the doors open for you, okay? I can't expect oxygen to be holding wall and then holding the other side and then trying to go in and out of the capillary, right? So something has to keep the alveoli open at all times in order for the gas to be able to exchange. That's why nitrogen is so high. Okay, that's its job, to hold open the alveoli at all times. Okay, so 592. So nitrogen is 592.8 millimeters of mercury. Then we have argon. Argon is 0.93. So argon is 0.93. Argon is 0.93%. So that's 760 times charisma. What number do I put right here for charisma?
You said 2 places to the right, right?
Yeah.
93.
Left, baby. 2 places, move the decimal.
Oh, 0.0093.
Point 0093. Excellent. Now charisma, 760 times 0.0093 is what?
It's 7.06.
0.06 millimeters of mercury. The pressure of argon. See that? P big, that's a big P. Pressure of argon. So the pressure of argon is 7.06 millimeters of mercury. So 7.06 millimeters of mercury. And then, of course, trace gases. Yeah, so that would be trace gases. Trace is 0.01%. So that would be 760 times what?
0.0001.
Pressure of trace gases is how much pressure is trace gases? The farts of the world. How much pressure are they exerting in the atmosphere?
0.076.
So 0.076 millimeters of mercury. 0.076 millimeters of mercury. So this is what it's showing you. Dalton, this is Dalton's law. He says if you add up all of the individual ingredients of the barometric gumbo, right? They're going to give you one barometric pressure, which is 760, right? That's what they're going to give you. But he says if you each one has its own individual pressure. Okay? If you take it out, he got his own pressure. All right? And that's how you find his pressure, by taking him out and multiplying him by the total barometric pressure. So let's look at it. Let's test our theory. Looking at this right here, looking at this, if I add up these barometric pressures, what do I get? Add those up. Tell me what you get. I don't know why Siri is talking to me. I ain't talking to you. You're telling me about barometric pressure. So if I add those up, guys, what do I have? 759.164. So 760 millimeters of mercury. Okay. Got it? Any questions on how I got this?
Yes, I got a question. How did you get this?
Right here,
Yes, sir.
add these pressures up. 159 plus 0.228 plus 592.8 plus 7.06 plus 0.076 equal 759 point something. We just said 760.
All right.
That's Shakira.
Yes, sir.
Yeah, but what we did you see how we got these numbers right here, Shakira?
Yes, sir. But
Okay.
That's why when I added it, I didn't put the 0.228. That's why I missed it.
Oh, okay. That is barometric pressure. Dalton's barometric pressure. Okay. Now, I hope that barometric soup helped you understand how he's explaining his theory or his law. Okay? That's how he explained his law. That's what he says. Okay? And now, you need to make sure you understand that because there's going to be a lot of time we're going to talk about barometric pressure, and sometimes it's not 760. Right? Remember when we do the P big AO2? Sometimes the barometric pressure is higher or lower. Right? What about, so at barometric pressure, let's just say, so at a P bar of 760, the normal P little a O2 in the blood is 80 to 100 millimeters of mercury, right? The normal P little a O2 is 80 to 100, correct? All right, that's at body, sea level and normal barometric pressure. That's what that is. Okay. So how can I make this more in somebody? How can I make the oxygen become super saturated? Huh? Yeah, giving them more. No, not ventilation. Giving them more oxygen. Don't forget, ventilation and oxygenation, two different things. If I want to give somebody more oxygen, I give them more oxygen. Okay. But what I'm trying to get you to understand is, what if I'm already giving them all the oxygen I can give them and it ain't working? What can I do now to make the ability of the oxygen become stronger?
Give more nitrogen?
Oh? You said Ebola. Oh. What somebody say? Speak up. I can't hardly hear you.
Lower the pressure.
There you go. Lower the barometric pressure. But not lower it, but you go lower, and what happens? This goes up. Remember? Sea level. Going deeper. Right? So, 760 is the barometric pressure, also known as the AKA 1 atmos. 1 atmosphere. That's what we are now, 1 atmosphere. Sea level is also considered to be 1 atmosphere. So at 1 atmosphere is 760. And we said 0.21 times 760 gave us 159 millimeters of mercury, right? Of oxygen pressure pushing at your tissues, okay? But what if I'm giving them oxygen and it's not enough? Then what we can do what's called hyperbaric chamber, right? Where you take the patient deeper in the atmosphere, in a little chamber that looks like a submarine. It's called a hyperbaric chamber. And we can take them down to a deeper filling, right? Which is 2 atmospheres, right? Or 3 atmospheres. So what would the barometric pressure be at 2 atmospheres if 760 is 1? 1520. Everybody see that? Barometric pressure at 1 is 1 atmosphere is 760. But if I go deeper and go give you 2 atmospheres, now that doubles the barometric pressure. Now it's heavier. Remember, the farther you go down in the water, the heavier the water gets, right? That's why when divers go real deep, sometimes their little glass thing pop or combust in. If they lose their pressure suit, their whole body can shrink in like a can, right? Because there's so much pressure on them, right? So at 1 atmosphere, P-bar is 760. But if I take you down deeper to 2 atmospheres, so at 2 atmospheres, the barometric pressure is how much, Lord? 1520 millimeters of mercury. So at 2 atmospheres, the barometric pressure is 1520 millimeters of mercury. That's a lot heavier. Now, what is the oxygen pressure now at 21%? Instead of 159, it goes up to how much? Look at it. How much? Okay, so we said, let me see. All right. We already said to find the pressure of oxygen at regular barometric pressure was 0.21 times 760, right? 0.21 times 760, and you get 159. Remember that? All right. Well, I just said, what if I put them in a hyperbaric chamber and take them down 2 atmospheres? Okay. Well, now the barometric pressure at 2 atmospheres is 1520, because that's 760 times 2, or plus 760 plus 760, right? It's 2 atmospheres, 2 of those. So, Kenya, 760 plus 760 is what?
Does it not matter if we just do 159 times 2, or do we need to actually do the...
No, don't confuse it. How much?
760 plus 760.
Yeah. $15.20.
Okay.
So 2 of those. One of those, 1 atmosphere is 760. So 2 of them is 1520.
Okay.
How much would 3 of them be? 760 plus 760 plus 760, or 760 times 3. See what I'm saying? So it just keeps going. It's just showing you how it doubles, okay? So at 1 atmosphere, the pressure of oxygen, at 1 atmosphere, the barometric pressure is 760. We already learned it. And then we took all of the atmospheric gases and multiplied them by 760 to find out how much pressure each one of them is exerting, all right? Well, if I have somebody who's on oxygen, but it's not enough, we have to see how can we enhance the ability of that oxygen. And somebody told me we can take them deeper, right? 2 atmospheres. So now if I have 2 atmospheres, you said, it's 1520 millimeters of mercury. Now let's see how much the pressure of oxygen will be at 2 atmospheres, at 2 atmos. That will be 0.21 times 1520. What will that be? The pressure of O2 at 2 atmos will be how much?
319.2.
There you go, 319.2 millimeters of mercury. So is that more than 159? Mm-hmm. Yes, so it is pushing harder. So now the pressure inside of the oxygen pressure inside of the body is higher, right? It's way higher than if it was on sea level. Okay, that's what we call supersaturation. Supersaturating them with oxygen. Because when you're giving them oxygen and it ain't enough, and it's uncorrected hypoxemia, right? If we giving somebody 100% oxygen and their P little AO2 is still 60, that is uncorrected what? Hypoxemia. Well, damn, I can't give you no more than 100, right? If I got you on 100% oxygen, I can't give you any more. All right? So there's some other things I can do, but what we're talking about as it pertains to right now is make that 100% be doubled in what it's doing, right? By going down in the hyperbaric therapy, hyperbaric oxygen therapy. That's when we put them in this submarine-looking room and we take the pressure down inside, and it pressurizes the hyperbaric chamber to however many atmospheres you want. And that makes that little bit of oxygen that you did have even more stronger. All right? So y'all told me that the pressure of O2 at 2 atmospheres is 319.2 millimeters of mercury. So if I want to know specifically for Mr. Smith, right? So say I have Mr. Smith on, we got Mr. Smith on 100% FiO2, right? And his P little a O2 is only 50 millimeters of mercury. All right? I'm trying to see how I can do this. If I have him on 100% FiO2 and his PaO2 is only 50 millimeters of mercury at sea level, if I go down 2 atmospheres, then now I am going to double the amount of ability that oxygen can do. And that's going to raise his PaO2 up, okay? People can get PaO2s up to 1,500. P little AO2 can go up to like 1,500 millimeters of mercury if we need to, okay? By going deeper down lower. Because the lower we go, the heavier the water, right? You go down deep, it gets heavy on you, right? You still feel like I can't move my chest because I'm really, really deep. That's why when divers go deep, what do they do before they can come straight up?
They have to pause underwater.
They have to pause. They come up a little bit and decompress. Come up a little bit more, decompress. Come up a little bit more. Because if they go straight from 4 atmospheres to nothing, they're going to die from what's called decompression sickness, also known as the bends. And what happens is the nitrogen in their blood starts to bubble up. And then that's when you have bubbles all in your air, in your arteries and your veins, and that'll kill you. Okay, so when you watch the movies and somebody's diving, here comes a shark and they knock off the edge of the tank and ride the tank all the way to the top, that's movies. If he does that, he's going to be sick. Okay, so they have to come up slowly, 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 so their body adjusts to the less pressure. Okay.
Does that happen in airplanes too? When you're really high in the sky, would that happen?
Yeah, that's why if something happens and you're in the air, say you're at 35,000 feet, and some reason that the fuselage of the plane loses its conditioning, because they condition it to be the same all the way through, so you don't have to feel anything different. But if they lose the decompression in the fuselage, which is where the people sit, right? What pops down?
The oxygen mask.
Oxygen mask, because it's going to be hard for them to inhale. Because if the pressure around you is really, really low, you trying to get lower in order for it to come in, like you learned, right? It ain't coming. Especially at 37,000 feet, it's going to be hard to take a breath. Because you're pulling, but ain't nothing moving because you can't get lower than the outside air. Remember, you have to be lower in order for gas to move towards you. And so they give you some oxygen to help that decompression situation so you can at least be getting your oxygen until they fix the problem. Okay? So when I go up, then I'm making my barometric pressure lower, right? Instead of 760, it's losing, right? It's going down by 2. You know what I'm saying? It keeps going down and it becomes very, very light, no pressure at all. We want to be lower than the outside, right? That's the only way gas can move into my lungs is when I inhale, my intrapleural pressure becomes lower than atmospheric pressure. And at 760 and sea level, it ain't hard at all. All you gotta do is just breathe, right? But when you go up high, it's not so easy because the atmospheric pressure or the barometric pressure is lower than it is down here. And so now it's harder for me to pull that air in because it's lower. It's saying, how low can you go, right? So down here, you can just go right under it and breathe, right? It's easy. When you play how low can you go trying to get lower than the atmospheric pressure, you just kind of just go through and just breathe and you under there, right? But when you go up really, really high, it's like way down here. And then they say, no, you're going to have to work for this breath. So now you're going to have to get real low in order to get that breath. All right? All right, let's take a break. It is, let's just say it's 2:05. Come back at 2:15. Take a 10-minute break. Come back at 2:15. All right, guys, so I'm showing you this right quick, a little closer shot so you can, when you go back and look at it and pause it or whatever. Pretty much all this is showing you is, first I wanted to show you that barometric soup, which is talking about Dalton's law, right? This is my gumbo here, my pot of gumbo on the fire, okay? And inside of the gumbo is all of your atmospheric gases. We got argon, we've got nitrogen, CO2, oxygen, right? And trace gas. If you notice, it is pretty proportional to the amounts. A lot of N's because it's mostly nitrogen, right? The atmosphere is made up mostly of nitrogen, which is 78%, right? Okay. And each individual gas has its own pressure. And that's when we showed you when you take out O2, which is 21%, you multiply 0.21 by 760, you got 159. Same thing with nitrogen, carbon dioxide, argon, and trace gases to find the total pressure, which is the barometric pressure, which is Dalton's law. All right. The next thing you're going to start seeing are these other gentlemen's law, Boyle's law, Charles's law, and Gay-Lussac's law. Okay, Boyle's law, Charles's law, and Gay-Lussac's law. And we're going to learn more about them as well. But notice these parameters here: volume, pressure, temperature, volume, pressure, temperature. Okay. Temperature, pressure, and volume are the gas laws relationships. Okay, they're very, very important. Each law states how each one of these relates to another one. Okay, Boyle's law talks about the relationship between volume and pressure. Charles's law talks about the relationship between temperature and volume. And then Gay-Lussac's law talks about the relationship between pressure and temperature. Okay? Remember I said, when those things change, when that temperature changes, a lot of things can change. That's why we are so gung-ho about you knowing normal body temperature, because if somebody is febrile, things can change. Okay? If somebody is febrile, what does that mean? When somebody to be febrile, they have a fever, or they have a temperature above what? Okay, 98.6.
98.6.
Fahrenheit. Or 37 degrees Celsius. Excellent. Okay. When somebody, or the temperature outside, if that's different, it changes things. Okay. And so we're going to learn about those relationships coming up. All right. Share my screen. All right. So we already talked about barometric pressure. But what's the next thing that's in that alveolar air equation that we talk about? And that is the water pressure, right? Water pressure. And that is the pressure of the vapor that is in your lungs. Because when we inhale, how does the vapor get in your lungs? Because of the what? How does the vapor get into your lungs?
Nose.
The nose. The nose heats and humidifies dry gas. So when that dry oxygen and nitrogen and all that stuff is inhaled through the nose will warm it up and moisten it up, gives it a vapor in order for the lungs to use it. The lungs do not want dry gas. They don't want cold gas. They want 37 degrees Celsius and 44 millimeters of mercury pressure of water. That's what I want. That's what the lungs say they want. All right. Now, so that is the second aspect of the alveolar air equation. I told you this lesson kind of just breaks down each component of the alveolar air equation. Just breaking down the components. All right. All right, so we got P big A O2 equals. The markers are going out pretty quick on me. All right, P big A O2. Let's see here. All right, what's first? FiO2, which is the what? What is FiO2?
Room air.
No. It could be room air, it could be not. What is FiO2? What is it?
Supplemental oxygen or oxygen or
Not necessarily.
Fraction of inspired
There
air.
you go. It's the fraction of inspired oxygen, whether it's room air or I gave you a whole bunch, right? That doesn't matter to make the name. The name is the fraction of inspired O2, whatever that is that I inspired. If I'm just in room air, then it's room air, okay? But if I got on some oxygen, it's going to be a higher percentage. But it's still the fraction of inspired oxygen, okay? This is the oxygen that I'm breathing, whether it's room air or 1,000%, okay? All right, so that's the FiO2, which is the fraction of inspired oxygen. Hey. All right, let me try this marker. P bar is the what? Barometric pressure. The P bar is the barometric pressure. And now we know how we got to barometric pressure, right? We got the barometric pressure by using Dalton's law, which says that all of the gases of the atmosphere have their own pressure. And when you add their pressures up, they equal how much? 760 at sea level, right? That is the barometric pressure. Now, we're trying to figure out how much oxygen is in the alveoli. I don't want to know about CO2. I don't want to know about water. I just want to know the oxygen. And so this is how we're breaking it down to find out just the oxygen, right? They just want to know how much oxygen is in the alveoli from what you inspire. Okay, so we have to factor in how much we breathe in, whether it was room air, whether it was 30%, 40%, 45%, whatever it is. That's the FiO2. Now, we need to multiply that FiO2 by something, which is the total barometric pressure minus the what? What is that? What is that?
PHO2.
Pressure of water, or the pressure of water vapor, okay? The pH2O is the pressure of water vapor that the nose supplied, right? You breathe it in and the nose made it moist. And what they're saying is the nose will provide 44 milligrams of water, which exerts 47 millimeters of mercury. But we'll get into that one a little later. But that's how they got the 47. So the pressure of water is 47. Why do I want to subtract this? Why am I subtracting that? Why would I be subtracting the pressure of water? Because, yeah, the reason why I am subtracting the water pressure, because all I want to know is what? Thank you. All I want to know is the pressure of what? Alveolar oxygen. That's all I want to know. I don't want to know how much water is in the lung. I want to know the pressure of alveolar oxygen. So I have to take the FiO2, which is how much are they breathing in, okay, times barometric pressure minus water pressure, or water vapor, right? So I got to take that water vapor out, all right? Now I'm still subtracting. What's the next thing I'm going to subtract out?
PaCO2.
PaCO2. PaCO2. I don't want to know how much carbon dioxide is in the lung. All I want to know is how much. There you go. So I got to get rid of it. I'm getting rid of the CO2 as well, which is the CO2 divided by the RQ. Okay, that is the formula. So what that does is that tells me at a P-bar barometric pressure of 760, I can subtract 47 millimeters of mercury of water from that, which will leave me about 713, right? Also, I want to get rid of the CO2, right? So if we have a normal CO2 of 40 and divided by 0.8 is what? 40 divided by 0.8, 50, right? So that's 713 times, let's say if we're on room air, 0.21. 0.21 times 713 is what? So 149.73 minus 50 gives us a pressure of alveolar oxygen of how much? 99 millimeters of mercury, or you can say 100 millimeters of mercury. That is how we find it. That is what this is all about, guys. It is getting rid of what we don't want. All we want to know is how much oxygen is actually inside of this alveoli. The P big A O2. That's all I want to know. I don't want to know how much CO2 is in there. I don't want to know how much water is in there. I just want to know how much oxygen is in there. So I got to get rid of the water vapor. I got to get rid of the CO2 over the RQ, and that's going to leave me with the amount that is in the alveoli. That's what this next couple of slides is getting ready to show. It's showing you how it's breaking it down. This is what we're using. We're getting rid of what we don't want and leaving what we want to know. Okay? That's what we want to know. All right, so let's look at it. What we just did, and they're going to do it one step at a time. So water vapor, also known as humidity, okay, exerts a pressure. It has its own pressure. And so they're telling you how much. It says the partial pressure of water at 100% relative humidity and regular body temperature is about 47 millimeters of mercury. So we got to get rid of that because I don't want to know. I want to know just the pressure of oxygen, because that way I can see if that oxygen is going into the artery, right? Water vapor don't go across into the artery, right? Only the gas. So I don't care about the water vapor. I got to get rid of that because that's going to let me know, do I have a disease process, right? Is the amount of oxygen that is in my alveoli, is it readily transferring into the artery or the capillary, right? That is called the what? The difference between the two is called the what? What is the difference? The difference between the amount of oxygen in the alveoli and the amount of oxygen that makes it to the artery. What is that called?
PAA different gradient.
The gradient. There you go. The AA gradient. Okay. So if I leave CO2 in there and I leave the pressure of water in there, that's going to be a huge difference, right? It's going to be a huge difference. I got to get rid of them so I can see, is that oxygen making it cross? Okay. I don't care about the water. I don't care about the CO2. Is the oxygen making it from my lungs into my blood? All right. All right. So again, here goes Dalton's law again. If you just want to write it down, it says, the sum total of the individual partial pressures of gases in the atmosphere are equal to the barometric pressure, right? So PB, he's just showing you the barometric pressure equals the pressure of nitrogen plus the pressure of oxygen plus the pressure of trace gases. And now when they say trace gases, they're adding the trace gases and the CO2 together because they're so small. CO2 is 0.03 and the trace gas is 0.01, right? They're just very, very small. The main gases are nitrogen and oxygen, and the trace gases will be, in this case, the trace gases will be trace gases, argon, and CO2. The argon is real small too, right? That's not even one, right? And so they just kind of do that. But you don't have to remember this formula right here. That's not important, okay? They're just trying to show you that this is Dalton's law. He's saying his PB, which is barometric pressure, is sum of all of the pressures in the atmosphere, okay? Now, the pressure of each gas will be exerted when separated from the mixture. That's what I said. When you take the carrots out of the gumbo, you taste the carrots. If you take the shrimp out of the gumbo, you taste the shrimp, right? But when you put them all together, it has one flavor, Mama's gumbo, okay? All right, so let's continue to break it down. All right, this is a list of those gases here for your, for your notes. Oxygen is 20.95, so we just say 21. Okay, we say 21. Nitrogen 78.08, argon 0.93, CO2 0.03, trace gases 0.01. This next part right here is just simply showing you what I've already showed you. How do we take these and make them millimeters of mercury, right? So here's that example for oxygen right here. You take the partial pressure of a gas equals the P bar times the concentration, all right? Whatever concentration you're trying to find out. So for oxygen, the concentration is 21%. So that will be 0.21 times the P bar, which is 760, and you get 159 millimeters of mercury. So oxygen at sea level exerts 159 millimeters of mercury of pressure, right? Around you right now, everybody that's under the sound of my voice, around you, oxygen is pushing at your forehead. You remember when you used to get into fight and they used to put their finger on your forehead and say, and do you like that? Or you see somebody get done like that and they talking to them with their finger all in their forehead. That's what oxygen is doing to you right now. He's pushing at 159 at all times. How much is nitrogen pushing you? Good. Nitrogen is pushing at 592. So he's doing you like that, right? All day long. Okay? So that's what he's trying to show you. That's what he's trying to show you. Each one of those gases has its own pressure. You with me, Courtney? Courtney, you with me?
Yes, sir.
Okay. What about it's not Stephanie, but Stephanie's here. What about Miss Sydney? You here, Sydney?
Yes.
Okay.
Yeah.
All right. Miss Winston, you got me?
Yes.
Good so far. Okay. Kiara, are you understanding where we are right now?
Yes.
Heather, you good? Miss Herman, you here? All right. All right, so let's do what I've been talking about is that application of Dalton's law to the lung, and that's going into that the alveolar equation, showing you why we subtract different things. Okay, so let's look at it. The partial pressure, that's what we just said that, of oxygen is 159 because we did 0.21 times 760. All right, look at B. It says in the lung, the water vapor also exerts a pressure, right? And it's 47 millimeters of mercury. Thus, it changes the pressure of the atmospheric gases in the alveoli, right? It's going to change that pressure in the alveoli. So we got to get rid of that, right? If I had the pressure of oxygen and the pressure of water in there, that's going to make my number bigger, right? I got to get rid of the water vapor so I can see what is actually just the oxygen. Okay, it's not like panning for gold. You ever seen them people panning for gold? When they take some dirt in a pan and they put water in and they shake the pan around. They don't care about the rocks and the stalagmite and all of the mud. They don't care about that. All they want to see is that little bit of what? Gold. That's what we're doing. We're getting rid of the dirt. We're getting rid of the mud. We're getting rid of the rocks. All I want to know is the oxygen. Okay? So he's subtracting things. All right? So this is the example. P bar equals 760 minus 47. So we got to get rid of the 47. That leaves us with 713. Right? So now that leaves us down to the pressure inside the lung of 713. That's still too much. We still got to get rid of some more stuff, right? Look at C. Because of the change in barometric pressure in the alveoli, the partial pressure of O2 also changes. So now we don't do 760 times 0.21. We're doing 713 times 0.21. See that? And that's where we got 149. See that? We were doing, when you work out the problem, it's 760 minus the pressure of water, right? Well, now when we already do that, we take that pressure of water out, and now we're left with 713, because 760 minus 47 is what? 713. So now you have, look, pressure of oxygen inside the alveoli will be 713 times 0.21, which gives us 149 millimeters of mercury. See how we're deducting? We're going down and down. So we started out with 760 times, 760 minus the water pressure, right? We got rid of the water pressure, and now we're down to 713, right? And now 713 times, if they on room air, 0.21 is 149, okay? Now, I can't stop there. I can't say that the P big AO2 is 149 because I still have to get rid of that other gas, which is what? Carbon dioxide. You got to get rid of him. Mute your mic. Whoever just came in, mute your mic. So we still got to get rid of the carbon dioxide. So let's look at D. In the lungs, the CO2 is higher than in the atmosphere and is affected by the respiratory quotient, which is the unequal exchange of oxygen for CO2, right? So what we do is we have 149, and we got to subtract the CO2 divided by the respiratory quotient. Got to get rid of that. So the example is 149 minus 50 equals 99. So thus you are left with P big AO2 of 99 millimeters of mercury. That is if everything is normal, right? All normal values, room air, normal CO2, right? Normal RQ, normal P bar, right? That is how we get 99 millimeters of mercury. All right. So it's just what you've already been doing, guys. But what it's doing is showing you why we do what we do. Why are we subtracting the water vapor out? Right? We're panning, right? I'm panning for oxygen. I did a scoop of dirt, a big breath, right? I got a scoop of dirt with all of the different gases and everything else, right? I put a little water in it, and now I'm shucking that pan around, right? I get rid of the dirt. I'm getting rid of the water vapor. I'm getting rid of the CO2 and the RQ, right? And what I'm left with in that pan is little pretty sparkles of oxygen. Okay, and that's what I want to see. That is why we got rid of everything else. Okay, if you had a house full of people and you wanted to know who really loves you in the house, then you got to get rid of the folks who don't, right? You can't say all 20 people in this house love me. You got to say, no, this little 6 or 7 right here, I know they hate me, so I'm going to get rid of them. These little folks over here, they plotting against me, I'm getting rid of them. And then when you really look at your friend list, you only got a couple people who really, really down with you, right? So you subtract everything else, and what you're left with is the pressure of oxygen, okay? Can't make it any easier than that, guys. All right. So that is how we got the 99 millimeters of mercury for the alveolar air equation. Now let's look at E. It says the ideal alveolar gas equation, of course, it says in addition to the effects of water vapor on the partial pressure of gases in the alveoli, the carbon dioxide diffusing from the bloodstream into the alveoli will further decrease the alveolar PO2. So since carbon dioxide is leaving the bloodstream in a closed system and entering into the respiratory tract, which is an open system, there is an indirect relationship between the pressure of carbon dioxide and oxygen. It's just saying a whole lot to say what we already said, guys. So when that CO2 makes it from the blood into the open system of the alveoli, it's going to be exhaled, okay? It's on its way back out to the air. All right, so if that is true, then look at number 3. An increase in PaCO2 will result in a decrease in big AO2, right? If you got more CO, the more CO2 you got, the less oxygen you're going to have in there. It can only hold, you can't say if I pour this right here, you can't say if I can put both, I cannot put both of these bottles into one bottle, right? If I got CO2 and oxygen, I cannot pour all of this into this bottle. Something's going to get displaced, right? So if this is CO2 and this is oxygen, if I pour all this CO2 in, the oxygen is going to go out, right? It's going to come out. Two things can't occupy the same space at the same time, all right? You either love it or you hate it, okay? So that's all that's saying is that the higher the PaCO2 is, the lower your oxygen will be because it's displacing it, okay? It's displacing it, okay? All right, so if that's true, increases in your alveolar CO2 will result in decreases in your alveolar oxygen, of course, because it's only 100% in there. If you got more CO2 than you have oxygen, it's going to push the oxygen out, right? And vice versa, all right? Number 4, this indirect relationship basically involves only carbon dioxide and oxygen because they are the only metabolically active gases. Okay, what do I mean by those are the two only metabolically active gases? What does that mean? That oxygen and CO2 are the only metabolically active gases. What am I saying?
They affect, you know, like the way your organs work.
Okay. How are they related to metabolic? So how is oxygen related to metabolic, the metabolism? No, that's not what I'm looking for. Just tell me how oxygen.
Metabolism makes carbon monoxide.
Good. So carbon monoxide is a byproduct of metabolism, right? All right. So what is the relationship of oxygen and metabolism? What is the relationship between oxygen and metabolism?
Because if there is too much carbon dioxide being produced, I'm not sure.
Close, but no. You just told me, you guys, Michael, I think, told me that the relationship between CO2 and metabolism is that CO2 is a byproduct of metabolism. Okay, I'm looking for a simple answer. So if CO2 is a byproduct of metabolism, then what is the relationship for oxygen and metabolism?
Oxygen makes metabolism work.
Good. You need oxygen to have metabolism, right? You burn oxygen and carbohydrates, and that's metabolism. That's metabolization. The burning of oxygen and carbohydrates is metabolism, okay? Your metabolism. You're burning and using the oxygen and burning the sugar, right, the glucose, and that is making metabolism. And when you make metabolism, it makes a byproduct or waste product called carbon dioxide, right? So aerobic metabolism is the use of oxygen to perform or make the body be able to metabolize. If you don't have oxygen, your body cannot metabolize correctly, right? It can't metabolize. So that's all I was looking for. What is the relationship, right? So those are the two metabolically active gases. That's what that means. That means oxygen is always being burned and CO2 is always being what?
Produced.
Oxygen is always being used and CO2 is always being produced. That's what that means by actively metabolically active gases. So that's why we're focusing on just those two, because you know nitrogen is in there too, right? But we're kind of not looking at nitrogen, because nitrogen has one job, and that is to keep the alveoli open. Okay. All right. Dalton's law must be modified to account for the incoming carbon dioxide when applied to the alveolar gas. So it has to be modified by subtracting it out. And that's why we subtract it out. Okay. And this is it right here, of course, once again, what you've already learned. P big AO2 equals the FiO2 times the barometric pressure minus the water vapor minus the CO2 divided by the RQ. Already what you've already learned, nothing new. Nothing new. And of course, this tells you everything right here. PA is the pressure of O2 in the alveoli. In fact, let me make that a capital A just to be anesthetic. All right. PB is barometric pressure. pH2O is the water pressure. FiO2 is fraction of inspired oxygen. P big A CO2 is the pressure of CO2 in the alveoli. And the RQ is the respiratory quotient. All right. Now, some places will do a modification like this. What is this? What is this formula missing? The RQ. Sometimes they leave the RQ off. Okay. You don't have to worry about, is that the one or is that? Just know that some physicians will leave the RQ off when they're trying to do the P big AO2, the alveolar equation. Sometimes they leave it, sometimes they leave it off. If they leave it off, it's just a modification, right? Same exact formula, just don't have the RQ on it. You just subtract the CO2 and don't worry about the RQ. Okay, that's just what they're showing. But in both equations, the P little a CO2 is always considered equal to the P big A CO2 because of the rapid equilibration of carbon dioxide. How much faster? 20 times faster than oxygen. Don't forget that. CO2 passes that border 20 times faster than oxygen does. So the P little a CO2 and the P big A CO2 is about equal, because as soon as it gets there, it goes right into that alveoli. Okay, so that's what they're showing you. So, like I said, let me go a couple steps back. Let's review. This is what's happening, guys. We started off with a barometric pressure of 760. Of course, they're showing you that to find out the pressure of oxygen in the atmosphere, you do 760 times 0.21, which is 159. And when we apply it to the lung, we say, okay, we want to get rid of the water vapor. So we take the 760 minus 47 of water vapor, and now we have a new pressure of 713. That's a new pressure, okay? And then we take that new pressure and multiply it by the FiO2, and that gives us 149, right? That's what we keep getting when we do it, right? Now, on the other side of the equation, which is the CO2, we still have to get rid of that as well, okay? We get rid of the CO2 as well, okay? And so we do 149 minus the P little a CO2 divided by the respiratory quotient. So here it is. P, which if we have a normal P little a CO2, which is 40, right? 40 millimeters of mercury, divided by 0.8, always, every day, even twice on Sunday, will give you 50, right? So you need to start recognizing some of these numbers that you're always going to see. If everything's normal, you know it's going to be 713, and you know it's going to be 50 on that side. So it's, you know, all you're really doing is multiplying by that FiO2. It may be changed, okay? So just keep that in mind. It's not really that hard. The 47 is usually always the same. The barometric pressure is usually always the same, right? And the CO2 and RQ is usually always the same. So we take that 149 minus the 50, and we're left with an alveolar oxygen tension of 99 millimeters of mercury. All right. So then we said, yeah, well, that's the same thing. Okay. All right. Of course, if we have an increase in alveolar CO2, that's going to push out oxygen, of course, right? You can't have both being at 100%. One going to be more than the other. All right. So what they're saying here is Dalton's law must be modified, right, in order to account for that CO2. We got to get him out. We already got the water vapor out. Now we got to keep CO2 out if we just want to know the goal, right? We're looking for just the oxygen, right? So then we do that. We subtract the PCO2 over the RQ. And right here, they're just saying sometimes some physicians will leave off the RQ altogether, and that's considered to be the modified alveolar gas equation. Look at this. The ideal alveolar gas equation is all of this. That's ideal. That's including everything. But a modified one can also be done, which leaves off the respiratory quotient. Okay, so this is a modified. And then this is ideal. Okay, this is the ideal one you've learned, and then but you can leave off the RQ, and it's considered to be a modification of it, and that's that one there. And that's simply the alveolar air equation, how we got it. Okay, all we want to know, Miss Winston, when I do the alveolar air equation, all I want to know is the pressure of what? The P big AO2. All I want to know is what, Miss Winston? What am I concerned with? Maybe she stepped away. All right. Cassidy, what am I concerned with? All I want to know is what?
The oxygen in the alveoli.
Yeah, oxygen in the alveoli. Excellent. That's all I want to know. I'm panning I get rid of all it. So if all I want to know is the oxygen in the alveoli, then Jessica, what's one thing I got to get rid of? What's the first thing we get rid of? All right, maybe she stepped out. Kiara, what's the first thing we get rid of, Kiara? All right, Kelsey, what's the first thing we get rid of?
The P bar minus pH2O.
So first thing we get rid of is the H2O, the water vapor, right? Okay, Kenya, what's the second thing we get after we got the water vapor out? What is the next thing we got to subtract? We already took the water pressure away from the 760. That's the first thing we subtracted in the problem is the water vapor, which is the 47. Now, what's the next thing we subtract? Because all we want to know is the oxygen. So we got rid of the water vapor. What's the next thing we got to get rid of? PaO2? No. Maria, what is the second thing we have to get rid of? Shatara. All right, Lori. Carbon dioxide. Carbon dioxide. All right. So once we got rid of the water pressure, now we got rid of the carbon dioxide, and what we're left is the oxygen. Okay. So that's the alveolar air equation. You guys, I hope you guys are paying attention. This is a lot of information. Can you imagine if you missed today? What if I'm trying to record and it don't record? And there is no recorded version. You're just going to get all this on your own. Okay. You need to be present. It's too much to watch later or to just be in and out. All right, let's take another break and we're going to come back and talk about the other gentlemen, Boyle, Charles, and Gay-Lussac, and talk about their gas laws. It's 55 after. Come back at 3:05. 3:05. I want to get as much of this in as possible. We might get knocked off a little early today, but come back at 55 after, and we'll resume right here at the ideal gas laws. All right. All right, guys. So we're going to talk about the 3 gas laws of that are very important: Boyle's law, Charles's law, and Gay-Lussac's law. All right. Then after that, we're going to knock off for today, because the next thing after that is going into the cylinders and how oxygen is carried, the color coding and safety systems. And I want to have the whole day to do that. I'm not going to start that, but I'm going to talk about that, these gas laws. And then after that, we're going to watch a video. Okay. And the video, this kind of like a little animation about the different gas laws. You're going to think about some things around your house that you say, oh, okay, now I understand where that law comes into play, and these little everyday things, okay? These everyday things. For instance, who knows if you have one of those things that spray your keyboard off with, your little can with the little stem, and you spray it, and it's a high pressure comes out of there real fast, and you spray your computer keyboard to get all that dust and stuff out of your computer keyboard, right? Who can tell me, as that pressure leaves the can and the pressure inside the can decreases, what happens to the how it feels in your hand?
The can gets cold.
It's cold. So if the pressure and the temperature both go down, right? All right, so temperature and pressure both are going down. The pressure is leaving out of the can, and at the same time, the temperature is dropping. Well, that would be an example of Gay-Lussac's law. Gay-Lussac says that pressure and temperature are directly related. Pressure and temperature are directly related. What about when you go outside in your car in the morning and you get that little tire sign on your, how many of y'all are getting a little tire symbol that talks about the pressure in the tires, comes on in the morning, now that it's winter time? Does anybody know what I'm talking about? Okay. So when it's cold outside, the temperature goes down, and what happens to the pressure inside your tires? They go down. That is also Mr. Gay-Lussac. That's one of his laws. Okay, so that's what's going on. When temperature and pressure are directly related, that is going off of Gay-Lussac's law, which is pressure 1 divided by temperature 1 equals pressure 2 divided by temperature 2. So I'm going to use that, show you in the PowerPoint. Okay. Just wanted to make that example so you can see that example. All right, so here they are. Now, the ideal gas law just says if mass is constant, then pressure 1 times volume 1 divided by temperature 1 equals pressure 2 times volume 2 over temperature 2. Now, that is not really what we're worried about. I want you to be able to tell me about each one, okay? Boyle, Gay-Lussac, and Charles, okay? I just gave you a couple of household examples that you may not have, that you have seen, but you didn't know really what was happening. But now you know what's happening, okay? Now, let's look at Boyle. Now, these relationships only are true if the other components remain constant, okay? So when you see that remain constant, that's what they're talking about. When you get your oral card and they say, hey, question says, cite Boyle's law. You need to be able to cite it, all right? This is Boyle's law. He says that if temperature and mass are constant, then volume and pressure are inversely proportional. Boyle says if temperature and mass are constant, then volume and pressure are inversely proportional. Volume and pressure are inversely proportional. That's what Boyle says. So that means if volume goes up, then the pressure got to do what? Go down, because they are inversely related. Okay? If the volume goes down, the pressure gonna go up. They are inversely related. That is Boyle's law. And I give you a hint. Boyle's law is the only one that is an inverse relationship. The other two are proportional relationships. They're directly related. Boyle is the only one that's indirectly related. So when you see indirectly related, you already know they're talking about Boyle. All right, let's look, and the formula for that is P1, which is the pressure number, the first pressure times the first volume will equal the second pressure times the second volume. P1 times V1 equals P2 times V2. That is Boyle's law's formula. You need to know the formula and the definition. So you might want to make note cards. So I'm getting those note cards, and when you're studying, hopefully you're making some. I haven't been requiring you to do it, but they're always good to make flashcards, okay? So that's Boyle's law. Well, let's look at Charles's law. Charles's law says that if pressure and mass are constant, then temperature and volume are directly proportional. If the pressure and mass are constant, then the temperature and volume are directly proportional. So that means if the temperature goes up, the volume goes up. If the volume goes down, the temperature goes down, according to Charles. The formula is V1 over T1 equals V2 over T2. Volume and temperature. I had one student said Charles is always watching TV. Charles is always watching TV, T and V, right? Temperature and volume. Charles is always watching TV. Okay. All right, and then lastly, we have Gay-Lussac, a gentleman, French physicist named Jean-Claude, I think Gay-Lussac. I think that's his first name, I'm not sure. But Gay-Lussac says that if volume and mass remain constant, then pressure and temperature are directly related. So Gay-Lussac says pressure and temperature are directly related. That's what we just talked about that can. When you spray that keyboard spray, when you spray it, the pressure is dropping out from inside the can. And not only is the pressure decreasing, but the temperature of the can in your hand is decreasing right in front of your eyes. Pressure go down, temperature go down. Pressure goes up, temperature goes up. When it's very, very cold outside, that's a low temperature. The pressure inside your tires seems to go down. Okay. When it's hot outside, the pressure in your tires increase. Okay. Those are examples of Gay-Lussac. The formula is P1 over T1 equals P2 over T2. And we use the triangle to demonstrate the relationship. Okay. We use the triangle to demonstrate that. So you need to be able to write that triangle so you will see what is actually happening. So look right here. Boyle's law says volume and pressure are indirectly related. So you see arrow going up on one side, down on the other side. Okay. They're inversely related. Volume and pressure are inversely related according to Boyle. All right. According to Charles, temperature and volume are directly related. Temperature and volume are directly related according to Charles. And then according to Gay-Lussac, pressure and temperature are directly related. Pressure and temperature are directly related according to Gay-Lussac. All right. What about Dalton's law? Dalton's law says that each one of the atmospheric gases exerts its own pressure. So the sum of all of the pressures equal one barometric pressure. That is Dalton's law. What about Avogadro? What does Avogadro say? All these should be on your law sheet with Laplace and Poisson, right? All your law sheet. What does Avogadro say? Avogadro.
1 mole of gas at STP occupies 22.4 liters.
Good. So he says 1 gram of any substance occupies 6 times 10 to the 23 or something like that, which is considered to be 1 mole. That's why we say Avogadro the mole. All right. And he says 1 mole will occupy 22 point something liters of volume. That is Avogadro's law. Okay. I told you guys you should have a sheet with formulas, a sheet with laws. Make sure you put them together because it's going to be hard to remember, 3 weeks from now, where you put Charles's law at. You need to be on one sheet, a law sheet. Okay. So those are the laws that you've learned today. You've learned Dalton's law. You learned Avogadro's law. You've learned Boyle's law. You learned Charles's law and Gay-Lussac's law. You learned that the atmosphere is made up of several different gases, right? Which are here. Those gases exert their own pressure, and you found out how to show me what their pressure is, right? By multiplying by the barometric pressure, okay? Remember, when you do your percentages, you have to change these percentages into decimals by moving the decimal place 2 places to the left. Then multiply by the barometric pressure, and that's how you got your pressure for each one, okay? When you add up those pressures, we added them together, and we came up with about 759 point whatever, okay? So 760, right? We learned that the alveolar air equation main job is to show me, the RT, how much oxygen is actually in the alveolar, not the CO2, not the water vapor, not the argon, not none of that. All we're concerned with is how much oxygen is there. And the reason why we use oxygen and CO2 is because there are the only 2 gases that are actively participating in metabolization. Oxygen is used to make metabolization, and CO2 is produced as a byproduct of metabolization. That's how they're related to metabolism. Okay? So don't let it confuse you. Go back, study, and read. Okay? The syllabus has the chapters for this. Read. Now, let me show you this other thing here. Shakira, I scooted it up so when you watch it a little bit later, you can see everything. I got close for you to see it, okay? All right. Now, I'm going to show you this. Okay, good. I'm going to show you this quick video, and I can't record, so the video is in the module, okay? The video is in the module, I think. Let me make sure. So I'm going to stop recording and watch the video. The homework for tonight is a sheet that I made up. Okay, it's a comprehensive homework practice 2/21. It's now in the module, due by midnight. It is a comprehensive worksheet. Okay, it's gonna have some stuff from A, B, C, D, whatever. It's not that many, maybe 20 questions, something like that. Make sure you guys are going back and studying your old assignments. We've been kind of busy with what we had, a lot of information to give you, so I haven't been able to go back as much. You got to go back on your own. So tonight, work on that sheet that I put it in the modules. When you click on the homework, it's already been uploaded to there. You have to open up the homework, and then open up the document inside of there, complete it and submit it. Okay. So I attached the assignment to the homework label. Okay. So let me show you this. If you need to go, that's on you. If you don't want to watch it, you don't have to. You can watch it later. But it's a little animation that kind of explains the gas law. So you can say, oh, okay, I see that. That's now I understand what that actually has been happening around me. Okay. But that is the homework that's already been put in there. And then we work tomorrow. Tomorrow we are going to go over the actual cylinders. We're going to put this stuff to rest. We're going to go over the cylinders, the actual oxygen cylinders. Okay? Actual oxygen cylinders. This happens to be a E cylinder. You got an H cylinder that's huge, right? And we have several types of cylinders, and they have safety systems, right? Color coding. A green cylinder is oxygen in America, but oxygen is white everywhere else in the world. Okay, a white cylinder would be oxygen anywhere else in the world, but in the United States, oxygen is green. Okay, but what if you are colorblind and you can't see colors, right? There are other safety systems that will allow you to not put the wrong tank on somebody, because somebody gets to breathe in nitric oxide, it'll kill them, right? So you have to have safety systems. We will talk about that tomorrow. So I'm going to show this video and I'm going to end the lesson for today. If you don't want to watch it, you don't have to, but I'm going to stop the recording so that I can show it. Homework has been put in. And so for those who leave, I have to see you tomorrow. And we'll also need to see you guys coming to class. I only have 2 at the most coming to class every day. You need to be in class, even if you're live. But if you're at home and you're live, you need to be here and live. Okay, you really do. All right. See you guys tomorrow. I'm going to stop the recording now, show the video, and then I'm going to end.